How do you picture an atom in your mind? Like this, or like this? If you understand enough about atoms to visualize any of those things, then you know more about atomic theory than scientists did just 100 years ago. And like way more than they thought they knew 2,500 years ago. That's when Greek philosopher Leucippus and his pupil Democritus first came up with the idea that matter is composed of tiny particles. No one knows how they developed this concept, but they didn't think the particles were particularly special. They just thought that if you cut something in half enough times, eventually you will reach a particle that can't be cut anymore. They gave these particles the name atomos, which means uncuttable or indivisible. So basically, they thought that a piece of iron was made up of iron particles, and clay was made up of clay particles, and cheese was made up of cheese particles, and they attributed properties of each substance to the forms of the atoms. So they thought that iron atoms were hard and stuck together with hooks. Clay atoms were softer and attached by ball and socket joints. That made them flexible. And cheese atoms, on the other hand, were squishy and delicious. Now, this makes a certain amount of sense if you don't happen to have access to electron microscope or cathode ray tubes or the works of generations of previous scientists. Because the fact is, atomic theory as we know it today is a product of hundreds, if not thousands, of different insights. Some models like that of Democritus were just blind guesses. As time went on, many more were the result of rigorous experimentation. But as has been the case in all of science, each scientist built on what had been learned before. Now you might think that once Leucippus and Democritus came up with the general idea of atoms, it will be pretty easy for someone else to take that little indivisible ball and run with it. But you'll be wrong. The next major development in atomic theory didn't come along for nearly 2,300 years. In the early 1700s, a French husband and wife, scientific duo, Marian and Antoine Lavoisier, studied and built upon the work of their Arabic predecessors. They found that certain pure substances could be broken down even further through chemical reactions. Water, for example, can be boiled into steam, which is still water, and can also be split into two gases, hydrogen and oxygen. No matter how hard the couple tried, they could not reduce oxygen or hydrogen into simpler gases. They concluded that the gases must be elements, which are foundational substances that cannot be created by mixing other chemicals together and cannot be broken down any further. With this concept in mind, scientists everywhere began searching for and listing as many elements as they could, eventually discovering all 118 listed on the modern periodic table. Some, such as oxygen and hydrogen, are gases at room temperature. Others are solids, such as elemental carbon and gold. Others still are liquid at room temperature, mercury and bromine. It was also found that under the right conditions of pressure and temperature, certain elements will react with each other upon mixing to form new substances. These substances would also have new properties. These are what we call compounds. The elements oxygen and iron can react to form a brown powder. I am sure you know it as rust. Oxygen and mercury react to form a toxic orange powder. Oxygen and hydrogen react to form a clear, refreshing liquid, water. Though the steps may be complicated, all of these reactions can be reversed. Elements can be reseparated, and the amount of each element we get back after separation is always equal or exactly equal to the amount that are reacted to form the compound in the first place. Wonderful. Elements are real and they appear to be essentially indestructible. But what are they made of? If you zoom in on a chunk of pure gold, for example, can you just keep zooming in forever and ever, seeing nothing but pure gold for infinity? In the early 1800s, a school teacher from England named John Dalton grew fascinated with chemistry, along with conducting several experiments of his own. He read about every experiment he possibly could find, paying special attention to the quantities of each element used up in every chemical reaction. He was surprised to find a pattern emerge. When two elements can react to form multiple types of compounds, they always do so in small whole number ratios. In this example here, we see that in order to transform a gram of carbon into pure carbon monoxide, we need to add 1.33 grams of oxygen. To turn a gram of carbon into pure carbon dioxide, we need to add exactly twice as much oxygen. That's 2.36 grams. These and many more other similar observations strongly suggest that oxygen and other elements are made up of tiny indivisible units, atoms. It is these units that combine when elements go into reaction. Dalton didn't know exactly how small an atom was, but the numbers suggested that the atoms of a single element were all identical in size to each other, but different in size to the atoms found in other elements. In 1808, he wrote a 560-page book that briefly mentioned his discovery. It even came with some quite beautiful drawings. While scientists weren't fully convinced that atoms were real, they did find the concept of atoms extremely useful. It helped them make accurate predictions and perform cleaner chemical reactions. In 1905, Albert Einstein proposed an experiment and produced an equation that could be used not only to confirm the existence of atoms, but to determine exactly how big these atoms are. A few years later, French physicist John Perrin used Einstein's concepts to actually do the experiments, confirming beyond reasonable doubt that atoms do in fact exist. Now, if you happen to love maths and possess an in-depth understanding of physics, then great. You can just go right now and go read his book. But for the rest of us, a little visual confirmation that atoms actually do exist would be nice, right? Yeah, the eyes have it. Unfortunately, individual atoms are far too small to be seen with normal light. The wavelength of light is just too great. This means that normal microscopes cannot see atoms. In the 70s, a group of engineers led by Gerd Binning and Heinrich Hoher began working on what they called the scanning tunneling microscope. A microscope they hoped would let us take undistorted images of many different types of atoms. It uses a process called electron tunneling to scan and essentially feel the surface of the samples, much like you can feel around in the dark to get a picture of your surroundings. This is an actual scan of silicon atoms forming the surface of a crystal. The colors here are artificial, but this is real data showing the actual pattern of silicon atoms arranged in the sample. Later work by Dr. Wilson improved this technique and cleaned up the presentation of data. Today, scientists at the National Science Foundation's Castle Research Center discovered a way to use actual light to see atoms. In the past, this was thought to be impossible because the wavelength of light is so much larger than an atom, but by shooting light at the tip of a probe, they were able to essentially shrink the light's wavelength and get it to scatter off the sample onto a detection screen. By moving the sample bit by bit, hitting it with light again each time, each pixel representing an individual data point from the scan, it will smooth it out, sharpen the edges, and change their chosen color scheme. It is shocking to find how close John Dalton's old drawings actually were to reality. Our species has finally done it. Over 2,000 years after Democritus first proposed the idea of an atom, we have now received direct confirmation atoms exist. I've already told you, for instance, about the French chemist Antoine Lavoisier, who proposed the law of conservation of mass, which states that even if matter changes shape or form, its mass stays the same. And you should remember the English teacher John Dalton, who determines that elements exist as discrete packets of matter. Thanks to these and other great minds, by the 1800s, we had a better grip on the general behavior of atoms. The next logical question was, why? Why do atoms behave the way they do? This led to the investigation of atomic structure. In the 1870s, scientists began probing what stuff was made of using discharge tubes, and these are basically gas-filled tubes with electrodes in each end, which emit light when an electric current passes through them. This is basically what a neon light is. Because this light was originally produced by a negative electrode, or what we call the cathode, it was called a cathode ray, and it had a negative charge. But in 1886, German physicist Eugen Goldstein found that the tubes also emitted light from the positive electrode, which is the anode. Basically, a ray headed in the opposite direction, which meant there must also be a positive charge in matter. Goldstein didn't fully understand what he had discovered here. I mean, scientists still hadn't figured out what was responsible for the negative charge in the rays either. Then, English physicist J.J. Thomson took the discharge tube research further by measuring how much heat the cathode rays generated, how much they could be bent by magnets, and other things. He was able to estimate the mass of the rays, and the mass was about 1,000 times lighter than hydrogen, which is the smallest bit of matter known at the time. He concluded that the cathode rays weren't rays or waves at all, but were in fact very light, very small, negatively charged particles. He called them corpuscles. We call them electrons today. So even though we didn't understand what shapes they took, we knew that they were both negative and positive components to matter. The next question was, how were they arranged in the atom? Thomson knew that the atom overall had a neutral charge, so he imagined that the negatively charged electrons must be distributed randomly in a positively charged matrix. And the very English Thomson visualized this model as a familiar English meal, plum pudding. The positive matrix being the cake and the electrons the random floating bits of fruits within it. Even today, Thomson's model of the atom continues to be called the plum pudding model. And while a single electron's motion is random, the overall distribution of them is not. The next big step was taken by New Zealander Ernest Rutherford in 1909. He designed an experiment using an extremely thin sheet of gold foil and a screen coated with zinc sulfide. He bombarded the sheet with alpha particles, which he didn't really know what they were, just that they were produced by the decay of radium. They were positively charged, and also they were really, really small. He expected them to just fly right through the foil with no deflection, and many of them did just that. But as it turned out, some of the particles were deflected at large angles and sometimes almost straight backward. The only explanation for this was that the entire positive charge of an atom, the charge that would repel an alpha particle, must be concentrated in a very small area, an area that is called the nucleus. Because most of the alpha particles pass right through the atoms undeterred, Rutherford concluded that most of the atom is empty space. And he was correct. Rutherford would later discover that if he bombarded nitrogen with alpha particles, it created a bunch of hydrogen ions. Now, it correctly surmised that these tiny positively charged ions were themselves fundamental particles, protons. Now we are getting closer to reality. So these chemists had a fairly good idea of the structure of the atom. They just needed to figure out what exactly the electrons were doing. In 1911, the same year the results of Rutherford's Godefroy experiments were published, Bohr traveled to England to study with Rutherford, and as a physicist, he was also interested in the mathematical model set forth by German physicists Max Planck and Albert Einstein to explain the behavior of electromagnetic energy. Over time, Bohr came to realize these mathematical principles could be applied to Rutherford's atomic model. His analysis of the Godefroy experiment and calculations based on the proportions of the alpha particles that went straight through, those that were slightly deflected, and those that bounced almost completely backward, allowed him to predict the most likely positions of electrons within the atom. Bohr's resulting model, sometimes called the planetary model, is still familiar to most people, probably including you. It represents the electron in orbits around a small central nucleus. Each orbit can have a specific number of electrons, which correlates to the energy levels and orbitals in the modern model of an atom. And while it's definitely flawed, Bohr's model is very close to reality in some very important ways. But like everyone I've mentioned in the past couple of minutes, Bohr was at once fantastically right and way off. The problem was those pesky electrons. It was the German theoretical physicist Werner Heisenberg who got everyone to understand just how huge and mind-blowing this electron problem was. But he was also the one who helped tie the whole mess up into a neat little bundle. Using his wicked math chops, Heisenberg discovered that it is impossible to know with certainty both the momentum of an electron or any subatomic particle and its exact position. And the more you know about one of these two variables, the harder it gets to measure the other one. So if you can't measure the position or momentum of an electron, you obviously can't say with certainty that the electrons in an atom are all neatly aligned in circular orbits. So he and a new wave of physicists and chemists proposed a new theory, a quantum theory which proposes that electrons weren't particles or waves. Instead, they had properties of both and neither. By this thinking, the arrangement of electrons around a nucleus could only be described in terms of probability. In other words, there are certain regions where an electron is much more likely to be found. We call these regions orbitals, and that's the modern understanding of atoms. Because it is based on probability, quantum atoms are often drawn as clouds with the intensity of color representing not individual electrons, but the probability of finding an electron in any particular position. For this reason, the quantum model is often called the cloud model of the atom. And now you know, all the people I've mentioned and many others put their heads together over time to build this current and I might say quite elegant understanding of the atomic theory. After 2,500 years, even though we can't see atoms, we can know what they are like and how they work, because a long succession of scientists contributed bits and pieces to the whole fantastic picture. But it's also important to recognize that we still may not be quite all the way right. Thomson's contemporaries were sure that the plum pudding model was right. Scientists in Bohr's day fully believed that the planetary model was right, and today we are extremely confident that the quantum mechanical model is correct, but it may not be all the way correct, and that's where you come in. The only way we can go on being sure is to keep asking questions and conducting experiments. And that's why you are taking chemistry and physics. If you paid attention in this lesson, you learned that Leucippus and Democritus originated the idea of atoms nearly 2,500 years ago. But that the real work didn't really begin until both protons and electrons were discovered by experimenting with discharge tubes, and how Ernest Rutherford figured out what and where the nucleus is. You also learned that chemistry can sometimes be done with just math, like how Bohr figured out his model, or the way that Heisenberg used math to usher in the quantum theory of the atom. Do send me your questions and your comments so that we can relate over this topic in the comment section. I look forward to discussing this lesson with you.